Okay, so today we'll be discussing about Gauss theorem. Now it has been formulated by Carl Friedrich Gauss in the year 1835, and this is one of the most important theorem in electromagnetism. Okay, it has also been included in one of the equations of Maxwell's laws of electromagnetism. Okay, so later on we'll study about Maxwell's law, Maxwell's equation. But today, before going into this Gauss theorem, we will be discussing a few physical quantities in order to understand Gauss theorem more clearly. Now, we have already studied in earlier topics that we have these two types of charges, positive and negative, and how this positive negative charges generates an electric field, okay, at the vicinity of these charges. All right. Now, for instance, this is my plus Q charge, and he is generating a radially outward electric field, and this is my minus Q charge, and he is generating a radially inward electric field. Now these arrows which you see here, these are nothing but my electric field lines due to this plus Q charge, and these are my electric field lines due to minus Q charge. Okay, now for instance, let us consider that this is a circular surface, even though it is seen as an ellipse, but this is kept in a three-dimensional 3D effect. So that's why this is not an ellipse, but it's a circular surface. And if I allow some field lines passing through this surface, okay, and if it is asked that how many number of field lines are passing through this circular surface, okay, so by looking into the figure, and if we count this number of field lines, we can actually tell that how many field lines are passing normally through this surface. Like in this case, it is how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 number of field lines are passing through this circular surface normally. Okay. So this number of electric field lines passing normally this through any surface, this is termed under the physical quantity known as electric flux. Right? Now, in actual practice, it is not that easy. You cannot see electric field lines. So since my electric field lines are nothing but my imaginary lines, so it is really impossible to visualize them. But still, then we can actually find out how many number of field lines are passing through any surface normally. Okay, and how we can do that? We need to know the value of the electric field strength in a particular region and the value of the surface area through which those number of field lines are passing through. Okay, so if we know the electric field strength E and my surface area value, and if we do the multiplication of those two quantities, we can actually find out that how many number of field lines are passing through that particular surface. Okay, now in this case, that's what I mentioned it here. So if an electric field E passes normally through an area element del S. Now del S is the surface area value. Now in this case, if this is my blue shade surface, circular surface, and if I consider that the surface area of this particular surface is del S, then electric flux through this area is nothing but del phi is equals to E del S. So the multiplication of the electric field strength E and the surface area through which the electric field lines are passing through. Okay, so if you multiply these two quantities, we can actually find out my electric flux value. But remember, we are doing this for the case when field lines are passing normally through the surface, that means perpendicularly to through the surface. Okay, what if the field lines does not pass through the surface normally? Okay, like in this case, this is again my circular surface. Here also, electric field is passing through this surface, but in this case, he's not passing in the normal direction. Okay, that means he's not passing in the perpendicular direction. He's inclined to a particular angle there. Okay, now in this case that angle is theta, and it is made with the normal of the surface. Remember, this dashed line is nothing but my normal vector. Okay, normal or area vector. Okay, so theta is the angle between this electric field E and the normal vector. Okay, so now if it is asked that, how you will be able to find your electric flux value through this surface, circular surface. So here in this case, what we need to know is the component of this electric field, which is along the normal of this surface. Now in this case, it is E cos theta. Remember, we have already studied in class 11 that how to resolute a vector, how we can find the components sine theta and the components cos theta. So in this case, we'll be using the component of E, which is along the direction of normal vector. Okay. So if you know the value of this E cos theta, and again, we'll be using the area value of this surface. So if you take a product of these two quantities, E cos theta and del S again is nothing but the surface area of this area value of this surface. So if you multiply these two quantities, we will be again we will be able to find our electric flux value. Now if you arrange it and if you bring it in vectorially form, so we can see that it is nothing but a dot product between the electric field E and the surface area vector del S. Okay, now we have already studied in class 11 that when we dot product two physical quantities or two vectors, we always get a scalar quantity. So hence we can deduce that electric flux is nothing but a scalar quantity with SI unit Newton Coulomb inverse meter square. Now remember, from the very beginning, we have been stating that we are actually finding out how many number of field lines are passing through any surface. So it's just a number, right? We will be finding out only the number, how many field lines are passing through. So since we are discussing, so only the number part, so that's why it is nothing but a scalar quantity. All right. Now, if it is asked that what is electric flux, so you are going to mention it in very simple terms, like it is nothing but the total number of field lines passing normally. So this part is very important. So you don't need any number of field lines. You have to find those field lines which is passing normally through any surface. Okay, so that is termed as electric flux value. So this is how we express electric flux mathematically, E del S. And when you do dot product, so you get another extra factor, cosine function. Okay, and then this theta is nothing but the angle between area vector and electric field. We have already seen here in this diagram. Okay. Now, Gauss, what he did, he derived a relationship between this electric flux and the net charge enclosed by the surface. He derived a relation between these two quantities, and that relation is coined as or termed as or stated as, you can say, Gauss theorem. Okay, so in order to understand Gauss theorem, let us assume that this is my plus Q charge value, and this dashed line which you are seeing here, this is nothing but an imaginary surface. Okay, so this imaginary surface, in this case it is spherical in shape. So this imaginary sphere, he is enclosing this plus Q charge value from all the three directions. All right, which is again at a distance r, as you can see in the figure. Now this imaginary surface, we have a term for that, and it is known as Gaussian surface. Okay, so this Gaussian surface is actually enclosing this plus q charge value at a distance r. Now we have already studied earlier that how to find out our electric field strength due to this plus q charge value at a distance r. So it is nothing but kq by r square. K, it is nothing but 1 by 4 pi epsilon naught. All right, we have already studied these things. Now here our main aim is to find out how many number of field lines are passing through this Gaussian surface due to this plus q charge value. That is our whole aim is. Now in order to find out that value, first what we will do, we will take a small segment of this Gaussian surface. In this case, what you see here is this blue shade, blue circular shade. So this is nothing but a small segment of this entire Gaussian surface. All right. So we will first find out that how many number of field lines are passing through this surface, blue shade surface, and then we are going to integrate and we are going to find out our entire electric flux value through this entire Gaussian surface. Now here ds is considered to be the surface area of this blue shade surface. All right. So if I find out my electric flux value, which is nothing but dot product of capital E and ds. All right. Okay, I have forgot to give the arrow here. So since we are doing dot product, so this arrow has to be there. Anyways, and if I use the formula EDS cos 0, now you see this why we have taken it as 0. Now the area vector of this blue shade surface, it is again radially outward. Okay, it is again radially outward. Now since we have already stated in earlier slides that theta is nothing but the angle between electric field E and the normal of the surface, right? So in this case, this electric field E and the normal, both of them are in the same direction. And that is why the angle between them is 0. So that's why we have written as cos 0 degree, which gives us a value E ds. So d phi, which is my electric flux. So why we have taken d phi? Because we are finding out electric flux only through this surface ds. All right. But if we want to know our electric flux value through this entire surface, entire Gaussian surface, we will integrate this d phi and we will be able to find our phi value. Okay. So here you can see that. So the net electric flux through the surface S is given by phi E is equals to integration d phi E. Okay. So d phi is the electric flux through that surface of area ds. Now you replace the value of d phi, which is nothing but EDS. Okay. In the earlier slides we have seen that. Yes. So d phi E is nothing but EDS. So you replace that EDS value. And then the next step we can see that since E is constant, so we have taken it out from my integration part. How this is constant? Now you see this electric field E, this is expressed as kq by r square. So this electric field strength will be validated over this Gaussian surface, right? Which is again at distance r. So if we find my electric field value E at this particular point, right, where my spotlight is located. So at this particular point, it will be kq by r square. If you want to know electric field at this particular point, it will be again kq by r square. If I want to know electric field value at this particular point, it will be again kq by r square. So over this Gaussian surface, my electric field value is constant. Yes. So that is why we have taken it out from my integration part. And the only variable which is inside the integration part is nothing but my surface area. So if you see this actually tells the total surface area of the sphere. Okay. Yes. So this is my total surface area of the sphere. You replace the value of the total surface area by 4 pi r square, and you replace the value of the electric field, which is again 1 by 4 pi epsilon naught q by r square. Right? And if you do the calculation, you will see that phi e is nothing but q by epsilon naught. Okay. So what we have understood is that if I take any charge, and if I want to know, and that charge is actually going to generate some electric field through this Gaussian surface, and if I want to know that how many number of field lines are passing through this Gaussian surface, we can actually find it out using this relation, which is nothing but q by epsilon naught. Now q is nothing but my net charge enclosed by the Gaussian surface. All right. So if you can find out what is your net charge enclosed by any Gaussian surface, you will be able to find your total flux value through that Gaussian surface. Okay. Now this is what I have stated. So Gauss theorem states that the total flux through a closed surface is 1 by epsilon naught times the net charge enclosed by the closed surface. Net charge, we need that value, right? So don't forget this part. Like for example, if you take a Gaussian surface, suppose if you consider a Gaussian surface, and if suppose you have 1 coulomb here, if you have 2 coulomb here, if you have 3 coulomb here, if you have 4 coulomb, and if you want to know that what is my phi value in this case, so you add all these charges 4, 6, 7, 8, 9, 10. So my net charge enclosed by this Gaussian surface is 10 coulomb. Sorry. Okay. So where was I? Okay. So this was my Gaussian surface. And if I take 1 coulomb here, if I take 2 coulomb here, if I take 3 coulomb here, if I take 4 coulomb, and if I want to know what is my net charge through this Gaussian surface, so all we have to do is just add them 4, 5, 6, 7, 8, 9, 10. So we have a net charge of 10 coulomb inside this Gaussian surface. So the Q value for this case, it will be 10 coulomb. So 10 by epsilon naught, 10 coulomb by epsilon naught. So that will be my electric flux value. Okay. So later on we'll be seeing the application of this Gauss theorem. We will be using this relation, Gauss theorem, and we will be finding out electric field due to an infinite wire. We will be finding out electric field due to an infinite plane sheet. All right, all these things we are going to derive in the next videos. Okay. All right. Thank you.